In this session, I will explain about pure inductive circuit. Let us consider a circuit in which a pure inductor of value L henries be connected across a voltage source which is represented by V. This is an AC voltage source, and let the current flowing through the circuit be represented by I. Then if we consider the waveforms of this, it can be plotted in this way, taking time along the x-axis and amplitude along the y-axis. Here the voltage and currents are represented along the y-axis, and this inductor has got the capability to generate EMF. It generates the EMF which is called as, it is going to induce the EMF due to the application of external voltage, that is V. So that voltage which is generated due to the effect of this applied voltage can be represented on the waveform, but that voltage will be opposite to the direction of flow of the applied voltage. So if this is the applied voltage which is represented by small v, then the applied voltage direction will always be opposite to the applied voltage. So this is the generated voltage which is represented by small v, small e. Then in a pure inductive circuit, the current always lags behind the applied voltage by 90 degrees. So if the current voltage has started here, the current will start somewhere here. So this can be shown in this way. So there is a phase difference between the voltage applied and the current. If this is the current waveform, dotted waveform is shown, that is the current waveform. When the voltage has already started, the current is not started, and it is going to start at 90 degrees from the initial point of the voltage, that is theta here. This is pi by 2. Theta here is pi by 2. The phase difference between these two is pi by 2. Pi by 2 minus 0 is pi by 2. And that pi by 2 is nothing but 90 degrees. So the phase difference between voltage, applied voltage and current flowing through the circuit is 90 degrees. And we can see that the same thing by making use of a phasor diagram, which can be denoted in this way. Let the current be denoted along the x-axis, which is taken as a reference. Then the applied voltage has already reached 90 degrees. See from this diagram, when the current has started, the voltage has taken its maximum value Vm. So this, the phase difference between applied voltage and current flowing through the circuit is always 90 degrees. And the induced EMF, generated EMF, is also 90 degree out of phase with the applied current, and that can be shown, but it is shown in the negative direction. This is the induced EMF, and this is the applied voltage. So this is how the phasor diagram can be represented. This is phasor diagram, and these are the waveforms. Now let the current be denoted by, let I be denoted by Im sin omega t. Then the induced EMF is given by small e, induced EMF, electromotive force, which is given by small e, is equal to minus L di by dt. Minus is taken because the induced EMF will always oppose the applied voltage, and it will be in opposite direction. And substituting the value of I from equation 1, this will be minus L d by dt of I is Im sin omega t. So this can be further simplified. Minus L, omega is constant, Im is constant, and differentiation of sin omega t is cos omega t. So this will be equal to omega L Im sin of omega t minus pi by 2. So this minus cos omega t is taken as sin of omega t minus pi by 2. And this shows that the induced EMF lags the current by 90 degrees. Minus indicates it is lagging behind the current by 90 degrees. And we know that the applied voltage is always equal to the negative value of the induced EMF, and this is equal to minus omega L Im sin of omega t plus pi by 2. So from this equation can be represented as V equal to Vm sin omega t. Okay, so from this we can see that this quantity is called as Vm. So I can write here Vm equal to omega L Im. And we also know that Vm by Im, V by I is nothing but the inductive reactance, which is given as omega L. From this only Vm by Im, if I take, that will be equal to omega L. And we know the values of RMS values of V and I are given by V equal to Vm by root 2 and I equal to Im by root 2. So substituting these values in the above equation number 2, so Vm from this will be V by Vm is nothing but Vm equal to root 2 into V, and Im is equal to I into root 2 from this. Then if we substitute the values, Vm is what? V by, this is equal to Vm and this is equal to Im. So this is V into root 2 divided by I into root 2. Root 2 will cancel. So this will be equal to V by I and that will be equal to omega L. And this ratio V by I is called as omega L, which is also represented as XL. XL is the inductive reactance of the circuit. And inductive reactance of a pure inductive circuit is given by XL, that is equal to omega L, and this is also given by 2 pi f because omega is having the value of 2 pi f into L. This is all about the inductive reactance. And now coming to the current, we know what is V from this, and the current can be represented by I. I is given by the ratio of voltage to the inductive reactance of the circuit. So this will be equal to V divided by omega L. XL is nothing but omega L, and that is equal to V divided by 2 pi f L. Now let us consider the power. The power is given by P, that is equal to the product of V with I into cos of theta, and here this is equal to V into I into cos of the phase difference between current and voltage is 90 degrees. So cos of 90 degrees, cos 90 is equal to 0. 0 into anything is 0. So this power is equal to 0. Now coming to the power factor, which is denoted by PF. This is given by cos of theta, and cos of theta, the phase difference here is 90 degrees. So cos theta is nothing but cos 90, and that is equal to 0. And this is always expressed as lagging. The power factor of a pure inductive circuit is 0 with lagging 1. The current lags the applied voltage by 90 degrees. So this is all about the pure inductive circuit, its waveforms, its phasor diagram, its power and power factor. Now let us see the power waveform of a pure inductive circuit. Let this be the current waveform and this be the voltage waveform. Then power is represented for every quarter cycle. From here to here, the value of voltage is positive and the value of current is negative. Plus into minus is minus. So the power can be represented in this way. In this time duration from pi by 2 to pi, both the quantities voltage and current are positive. Positive into positive is positive. So power can be represented in this way. During the duration pi to 3 pi by 2, current is positive whereas voltage is negative. So plus into minus, minus. So the power will be in the negative direction. And during this time interval between 3 pi by 2 to 2 pi, both are negative. So negative into negative is positive. So this is the power which is drawn for one cycle, and the same will be repeated. And the average power here is always equal to 0. So the power consumed by circuit is equal to 0, or the average power is given by 0, and this is the omega t value which is taken along the x-axis, and this is the power waveform which is shown in the dotted manner. Thank you.